Welcome back to Physics Fundamentals. In this video, I want to talk about electricity. And I'm going to start this discussion at the very basics, make sure we're all on the same page, with the structure of an atom. At the center of an atom, there is a nucleus. That nucleus contains protons and neutrons. Surrounding the nucleus, there is a cloud of electrons. Right. Very aptly named, the electron cloud is where you find electrons. And you may have, depending on your previous experience in the sciences, seen a diagram that involved orbits that looks something like that, which is really a terrible depiction, but it's good enough for some purposes. We're not going to worry about any of that because the only thing we're really concerned about is electricity. And electricity comes from electric charge. Protons have a positive charge, electrons have a negative charge. Hiding out inside the nucleus are the neutrons. There's another type of attraction-repulsion going on inside the nucleus of an atom that lets all these positively charged protons hang around together, and the neutrons are the fuel that allows that to happen. But we're talking about electricity. We don't care about what's happening in the nucleus. We don't care about neutrons for the course of this video. All right, so we have protons, which are positively charged, all densely packed in this central nucleus. We have electrons, which are negatively charged, which are floating around outside of the nucleus. The key idea here in electricity is that if you have two objects that have the same charge, two protons or two electrons, they are repelled from each other. But if you have objects that have a different charge, a proton and an electron, for example, they are going to be attracted towards each other. As I said, there's this thing going on with the neutrons that causes all these positive charges to be in one place, and having all these charges in one place attracts the electrons to the nucleus, and that's how atoms form. But within the electron cloud, you have all of these negative charges, and they would like to get away. And they're not that tightly held together. So it is possible, and it's actually something that occurs frequently, for one electron to jump out of the electron cloud of one atom, and maybe it will jump into the electron cloud of another atom. There are a couple of interesting reasons why that might occur. Those reasons are the foundations of the study of chemistry. So a little bit beyond the scope of this course, but chemistry is all about why electrons might want to leave one atom and go to another. For our purposes, we're just going to accept that this is a thing that electrons are going to do. And we're going to take a look at what the electron in and of itself is going to do on that journey. The first example, the first illustration of this, is something you are very familiar with. Static electricity. I don't know when it will be when you're watching this video, but when I'm filming this video, it is approaching winter in southwestern Pennsylvania. We all have our furnaces on, and the dry air is something that allows static electricity to be a little bit more prevalent. So with the dry air, the electrons are happier to jump from one place to another. For example, from the wool carpet to your cotton socks as you rub your feet against the floor trying to shuffle around lazily as you walk from room to room in your house. That is going to cause an excess of electrons to build up in your body. Now, the human body is what's known as a conductor. A conductor is a material that allows electrons to freely move around from one place to another. So the electrons will start in your socks, they'll get into your body, they will transform around your body, and they'll look for a way out because there's too many electrons. There's a negative charge in your body. If you make the mistake of touching something that is grounded, like a sink faucet, those electrons will jump out of your body and into the sink faucet, where they will find a much more peaceful place of being, where there is less negative charge built up. And if you don't mind me personifying the electrons, we'll call them a little bit happier. In this course, that's an interesting idea, and that's something that we want to be able to think about. But I want to take that a step further. I want to work with electrical circuits. An electrical circuit is a pathway made of conductors on which the electrons can move around. An electrical circuit usually has some source of power. There are a couple of different sources of power that exist. In this course, I'm going to stick with an electrical current caused by a battery. This forms what's known as a DC current. In a DC current, you have electrons that are being pushed by the battery and running around in the circuit. One side of the battery has a negative charge, which repels the electrons. The other side of the battery has a positive charge, which attracts the electrons. And now that we've said that, we get to the place where every electrical engineer curses Ben Franklin, because Ben Franklin didn't understand what was happening on this scale. He had no idea what an electron was. But he was the first person who observed the behavior of electricity traveling through a material, when he electrocuted himself flying a kite in a lightning storm. He chose to name the pathway incorrectly, and so he described the current as going from positive to negative. Right. Electrons flow from negative to positive. The current is read from positive to negative. We call this the conventional direction of current. And, well, it's entrenched now. We can't change it. Maybe 300 years ago we had a chance, but it's too late now. All right. We're going to represent current using the variable capital I. I have no idea why we use that letter, but that's what we use. And we're going to measure current in amperes. An ampere is defined as a certain number of electrons passing through a point in a given period of time. We're not going to worry about those details, just we have this measurement of amperes that we use to measure the current, the rate at which electricity is flowing through a wire. Related to that, actually, I'm getting a little bit ahead of myself. I almost forgot that I wanted to mention that there is also a source of current called an AC current. AC current is notable because it is the most efficient way of transmitting electricity over long distances for a bunch of reasons that are beyond the scope of this course. And so AC current is what is flowing through the electrical outlets in your house. And that's why when you plug something like a phone charger into the wall, you have to put this big brick in, which converts an AC current into a DC current, which your phone is able to handle. Right. An AC current, instead of having the electrons all going in one direction, the power is transmitted by the electrons bouncing back and forth. So you just have this oscillating motion in the electrons, and that's a different way of transmitting electrical power. It's incredibly difficult to analyze, so we're going to more or less ignore it in this course, but I did need to mention it. It is a thing that exists. All right, so we're going to stick with DC current, which means we're going to stick with working with batteries. Let's go ahead and redraw this circuit in some clean space here. So let me go ahead and get my head out of the way at this point as well. All right, so here we are again. We have a battery, we have some current flowing through the circuit, and then the other thing that a circuit needs is some sort of a load. We're going to denote a load in a circuit by this squiggly line. Specifically, this squiggly line is something that in electronics we call a resistor. And there are devices that are specifically made as a resistor. There are times when adding resistance to a current is very important. For example, you need to put resistance before you put a light bulb in a circuit, because if you have too much electricity flowing through the light bulb, it will blow out immediately, and, well, there goes any use of that brand new light bulb. But resistance is more general than that, right? When you plug your phone into your phone charger and you start charging the battery is drawing power out of the circuit. And so it is causing resistance to the continued flow of electricity, right? Current is a loop. It leaves the battery, goes around the circuit, and comes back into the battery. It has to get through anything that's plugged in. The more that the thing that's plugged in wants to do, the more resistance there is to that current. All right, so we have a resistance. We're going to go ahead and label that R. In order to overcome that resistance, our battery has to supply a certain amount of energy to those electrons. We're going to call that amount of energy the potential. The variable for potential is V. No, that does not make any sense until you realize that it makes complete sense, because potential is related to energy, and for some reason we represent energy as U, so V is just the next thing. It also makes a lot of sense because we measure potential using the unit of the volt. A lot of people call this measurement the voltage instead of the potential, which is a horrible, terrible name, but we just can't get away from it, so we're stuck with it. Sure, whatever. And then the resistance over here is going to be measured in ohms. The symbol for current, amperes, is A, volts is V for potential, ohms for resistance. The symbol for that unit is the Greek letter capital omega, because it's a pun, and physicists at the time found that incredibly entertaining, so they kept it. All right, so we have these three ideas. We have a current, we have a potential, we have a resistance. There is a relationship between those three measurements. That relationship is called Ohm's law. And it says simply that V is equal to I times R. Every now and then we're going to need this equation in a different orientation. So if I just flip it over and then divide both sides of the equation by R, I can equivalently write that I is equal to V over R. If you are pursuing a career in electrical engineering, solving for R is going to be a useful thing. But for our basic understanding that we're looking for in this course, looking at V and looking at I are the places where we're going to be a little bit more interested. This equation also gives us the relationship between the three units of the volt, the ampere, and the ohm. Because if potential is measured in volts, and current is measured in amperes, and resistance is measured in ohms, we get that a volt is an ampere times an ohm, or that an ampere is a volt divided by an ohm. Or again, if you really cared, you could say that an ohm is a volt divided by an ampere. So with that, let's jump into a quick example. And again, I'm going to draw this as a very simple circuit. I'm drawing this as though that resistor is just a component whose job is to be a resistor, even though, right, practically speaking, this is a light, or this is a motor, or this is a battery that we're charging, or this is a computer, whatever it is. Right, there is something there that is causing a load, and we can measure the resistance of that load. We can look at our battery. Maybe we've plugged in a battery that is labeled as producing 6.0 volts. And we know our resistance. We know that this resistor is providing something like 1.2 kiloohms. We can look at the picture, right? Again, electrons get thrown out from the negative side and go into the positive side, but the conventional direction of current is out from the positive direction and into the negative direction. And so that's going to be my goal. I know current is flowing in this direction. I want to know how much current is flowing in this particular setup. And to answer that question, it's just going to be Ohm's law. So if I'm using Ohm's law, I need to know V, I, and R. Well, I is my unknown, V is 6.0 volts, R is 1.2 kiloohms, but in order for the units to work out, we do want to convert that from kiloohms into ohms, right? 1.2 kiloohms is 1,200 ohms, or 1.2 times 10 to the third ohms. Either way you want to write it. And then our formula, V equals IR, which I've already shown you, we can rearrange to write as I is equal to V over R. So we've got 6.0 volts divided by 1,200 ohms. My calculator is quite happy to tell me that this comes out at 0.0050. And if I have volts divided by ohms, that gives me a result in amps. And I could leave it like that. There's nothing wrong with that. But I also could notice that it would be a lot nicer to rewrite this in milliamps. This current is 5.0 milliamps. And that's a perfectly valid way of writing it. Again, I'm not necessarily picky about did you find the best SI prefix, but it's always something that's worth paying attention to. All right, a little bit of calculation here. Hopefully you find that this formula is not that bad to use. There's a lot of theory and vocabulary going on. Make sure that you are feeling more or less comfortable with all of those things. Thank you, as always, for joining me, and I'll see you in the next one.